And what I need you to notice from your graph, and if you use the standard viewing window, you should have something that looks like what I've got on the screen. Notice that we had a 0 at x equal -2. Well, there is an x-intercept at x equal -2 on that curve. And we had a 0 at x equal +2. There's an x-intercept on this equation at x equal +2. So the x-intercepts of the graph of the function correspond to the zeros of the function. That's an important idea. And the other thing I want you to notice is that the 0 where we have a multiplicity of 2, the graph comes up, touches the x-axis at -2, and changes direction. So it kind of bounces back off the x-axis. Where the multiplicity was 1, the graph actually crosses the x-axis. And we can generalize that to all multiplicities that are either even or odd. If you have even multiplicity, then the graph bounces at that x-intercept. Okay, so if the multiplicity is 2, 4, 6, 8, any even number, you can be sure that the graph is going to touch that axis and change direction there. If the multiplicity is an odd number, the graph will always cross the x-axis at that 0. So let's kind of summarize what we know already so far. If we have a function, f of x is -4 times x plus 1/2 squared times x minus 5 cubed. Okay, I want you to determine the zeros, their multiplicity, and what that means for the graph. Does the graph bounce or cross there at those x-intercepts? And I also want you to determine the end behavior. So pause the video again, do that work, and then restart it and see if you agree with what I've got. Alright, our zeros are going to correspond to the values of x we get when we set each factor equal to 0. So x equals -1/2, we'd get twice actually. So the multiplicity of that 0 is 2. And we'd have a 0 at x equal 5, and the multiplicity at that 0 is 3. So we've got one multiplicity that's even, so the graph will bounce at this x-intercept. The other multiplicity is odd, so the graph will cross at that x-intercept, at the x-intercept of 5. To determine the end behavior, you have to look at the leading term. The coefficient is going to be -4. Then you're going to have an x squared that comes from this factor multiplied by an x cubed from that factor. So we'll have x to the 5th power. The limit then as x approaches infinity for f of x will be -infinity. The limit as x approaches -infinity for f of x will be infinity. Now if we know the zeros and the multiplicity and can predict the behavior of the function at that x-intercept, and we know the end behavior of the function, we can sketch a reasonable curve. We're going to know what the x-intercepts are because those are the zeros. The only other thing you might want to take a look at is where's the graph going to cross the y-axis. So, because that's very easy to do. Plug in 0 for x and see what you get. I'll do that real quick. Let's see, we'd have negative 4 times 0.5 squared times negative 5 cubed. 125, if I did that right. So that y-intercept is pretty big. Now, let's do a sketch with what we know. Alright, so we have an x-intercept at positive 5 and at negative 1/2. So I want to make sure that I label my x-axis adequately. So there's negative 1, 1, 2, there's positive 1, 2, 3, 4, 5, there's 5. I'm going to have negative 1/2, positive 5. Okay, now I expect the curve to bounce at negative 1 and cross at positive 5, so I'm keeping that in mind. Now I'm thinking about the end behavior. The right end is that the function is approaching negative infinity, so that tells me that my curve's got to be heading down on the right end. Because the left end is approaching positive infinity, that tells me the curve's got to be heading up on the left end. I know it's going to touch the x-axis at 1/2 and 5. Curve's going to bounce at 1/2, which means it's got to come back up. It's going to have to change direction somewhere up there to come back down and cross the x-axis at positive 5. So our polynomial function might look something like this. Since we did take the time to find the y-intercept, and that's not real accurate, notice that you want to label your y-intercept. Please notice that I've not put any tick marks at all on the y-axis. I'm not really super concerned about what's going on with the y-axis right here. What I'm concerned about is, do you have the correct end behavior? Do you have the correct x-intercepts? Does the graph cross at the appropriate x-intercepts and bounce at the appropriate x-intercepts? One more thing we want to talk about in this section, that's the intermediate value theorem. Works with polynomial functions. And we've got 2 points on our function, a and b, and the function values have opposite signs. So the intermediate value theorem says then that if these things are true, you have a polynomial and f of a and f of b have opposite signs, there is at least one value c in between a and b for which f of c is equal to 0. This is a lot easier to make sense of if we draw a picture. So let's say this is f, this is a, b is over here. Maybe f of a is this negative value down here somewhere. So I have the point a, f of a there, and maybe up here is f of b. So the point b, f of b would be about right there. Now if you have a polynomial function, you know you have to have a smooth continuous curve that goes through these 2 points. For the curve to be actually smooth and continuous and actually go through these 2 points, your graph has to cross the x-axis. F of c is equal to 0 means 0 is an x-intercept. You'll notice that this value c we're talking about is in between a and b. Now if you're concerned a little bit by the fact that we said that there has to be at least one value, think about this. How could you have more than one value? Well, maybe this is a, f of a, and here's b, f of b again. And we might have a polynomial function that does this. It is possible for there to be more than one x-intercept, in which case you've got more than one value of c. Notice that each of those, we could call them c sub 1, c sub 2, and c sub 3. Notice that they are all three in between a and b.